Hello, everyone. Welcome to the 36th Surface Ventures keynote. Let me just bring up our intro slides. Fantastic. There we go. So please say hi in the chat and tell us where you're joining from. My name is Dr. Sam McMaster. I am the event manager here at Surface Ventures. We are a not-for-profit organization, and our mission is to provide world-class materials science education for academia and industry. Today, it is my pleasure to introduce Professor Ivan Petrov of the Materials Research Laboratory, the University of Chicago at Urbana-Champaign, USA. Ivan Petrov is a professor of physics now also at Linköping University, Sweden. He was a professor of materials science and the director of the Center for Microanalysis of Materials at the University of Illinois. He has published 350 papers and cited 24,000 times with a H index of 78. He is a fellow, an honorary member of the AVS, the 2015 AVS president, and in 2009 received the Bunshaw Award, and in 2013 the Thornton Award. He has served as the chair of the IUVSTA Surface Engineering Division from 2007 to 2022, and he is also an editor of the Journal of Surface and Coatings Technology. We'll bring Ivan on stage now to say hello. And whilst Ivan is loading on stage, I'd just like to take the time to thank today's partner, Data Physics Instruments. We'll have a short presentation from Sebastian Schaubach later in the event. We'll also be releasing some poll questions and handouts from Data Physics Instruments at the event. Let's have Sebastian on stage now, please. Good afternoon. It's just wait for Ivan to come on stage, and we'll set up the screen share for this event. Excellent. we can now, Ivan. Welcome to the stage. Excellent. Would you like to set up the screen share, and then we'll proceed and hand over to you for your talk. Okay, so we'll stay on stage for a moment. As soon as we can see your slides, everyone in the audience should be able to, and then we'll begin the event. Whilst we're waiting for the screen share to load, let me just release this initial poll question for the audience to answer.
Did you hear my hello?
Thank you. Okay,
Thank you.
Excellent, Ivan.
Thank you,
I can see your slides. So I'll now leave stage and hand over to you. Thanks.
Okay, hello once again. This is the more extensive title. I'm going to share some results with you on the use of metal ion irradiation for a low temperature growth of dense, hard, stress-free, and
Ivan, I'm sorry for
low-stress
interrupting, but it seems
ceramic
the
thin
screen
films.
share has stopped. Could you set it up again, please?
This is a joint work between University of Illinois and Linköping University, and most of the recent work has been done over the last decade in Greg Grzinski lab at Linköping University. And there will be many other co-authors in.
Not a problem.
So
yes.
I will start with
just a slight technical hiccup.
An overview.
Be back rolling in a moment. Thanks for doing that. Thanks everyone for for answering the poll question. For anyone who's just joined, you can find that in the polls tab. I'd just like to say great to see so many people joining from so many different places. We've got Sweden, Leeds, SKF in the Netherlands. Hello, Ben from Micromaterials. Okay.
Magnetron sputter deposition has been useful for many decades, the so-called
so
bias
just
sputtering.
gotten
And then I'll introduce the
so just as you were beginning this slide here. So yes, thank you.
Okay. The problem, yeah, okay, I'll have to close and open the PowerPoint again. So how much did you hear? At which point did you lose me? The outline. So I'll first explain briefly the mechanism of gas ion-assisted growth by sputtering, introduce high-power impulse magnetron sputtering, HiPIMS, as a source of energetic target atoms, and also the fact that there is separation between gas and target atom fluxes, which allow us to select one of them and do by synchronized bias. But HiPIMS actually has lower deposition rate. So the rest of the talk will be hybrid HiPIMS DC magnetron sputtering process, combining the benefits of both, and in two sections: light metal ions like silicon and aluminum to synthesize highly metastable transition metal nitrides. And the second section is heavy metal ions, the opposite, like tantalum and tungsten, for low temperature synthesis of dense, hard, and low stress transition metal nitrides. And finally, on discovery that we came across studying these metals, these coatings, Guinier-Preston hardening mechanisms is reported for the first time for ceramic materials. So here, contrasting DC magnetron sputtering and HiPIMS. They use the same target substrate configuration chamber, the same average power. But the DC, let me put the pointer here, uses and so like this power density is 10 to 50 watts per centimeter square. Types of ions, typical ones, lower deposition rate because some of the metal ions produce a lot of gas ions, like argon ions here is 2 to 3 orders magnitude higher than the metal ions. So we have thermal combination of thermal gas ions, neutral deposited ions, and high deposition rate. In HiPIMS, with the same average power, we pulse. Okay, it will be frequencies not the hundreds of hertz, but duty cycle is a few percent. That gives us peak powers 2 to 3 orders magnitude.
I'm sorry once again. It seems that there's some slight instability with the DC connection.
Okay, and that's brings completely. I covered this slide. In each pulse, we have an explosive
so that we don't
discharge.
have any interruptions to the presentation.
Okay,
do you mind if we swap to sharing slides from the platform?
So as model, drive away for ion-assisted growth. The gas we use, so we sodium chloride transition from cubic transition nitride, and primarily titanium nitride and titanium aluminum nitride.
So
because of their wide use in practice, but diverse application.
Okay, so
these are refractory materials with melting point titanium nitride above 3,000 degrees Celsius. So even at 500 degrees Celsius,
through the slides,
which is only 0.2 of the melting point, we get very poor films, as illustrated in this cross-sectional TM. Porous, rough films. And that's why they have been used, as I said, the model systems for ion-assisted growth. And I will use this to demonstrate to you titanium nitride, how metal ions affect the growth. And this is generally typical for many other nitrides that I have listed below, which is the cubic structure. Next slide, please. Okay, structural evolution is conveniently described by structure zone diagram. The first one was introduced by Moshchan and Demchyshin, Ukrainian scientists from Patton Institute, Kiev, for thermal evaporation, electron beam evaporation. And there, as a function of the homologous temperature, the ratio of the substrate temperature to the melting point temperature, and they're characterized by 3 zones at low, very low temperatures, no diffusion practically, rough and porous films, intermediate temperature surface diffusion. You have bulk-like properties with columnar growth, and at higher temperature there is bulk diffusion also. Evaporated film have like thermal energy, the condensing species. This is given in blue, like 0.2 eV. In the graph, they're very low compared to the red curve, which is for sputter deposited species, or the sputter from the target, with a peak of about several eV extended to tens of eV. So Thornton in the 70s proposed the Thornton diagram for sputtering. We again have the homologous temperature, but he added a gas pressure axis extending from 1 to like 30 or 40 millitorr. And in the high pressure range on the top side, the particles are thermalized, so Thornton diagram is identical to the Moshchan diagram. But as the pressure is lower, we preserve this high energy of the sputter particles, and it's also Thornton pays a lot of attention of the ions backscattered from the target, which is a big flux, especially for heavy targets, that bombards the substrate and produces this transition zone, which has bulk-like properties, but also stresses. So here we can use the pressure to control the energy of the sputtered and backscattered particles in the range of like 2 to 20 eV higher. And we use also the fact that we have plasma near the substrates to induce ion irradiation. In typical magnetron systems, the ion to metal flux ratio is below 1. And we can vary then the energy to some hundreds eV by controlling the bias voltage. And that's the power of bias sputtering that has produced so many coatings over the last, let's say, 50 years, widely spread. Next slide, please. So here I demonstrate the zone 1 structure, which is obtained at 38 millitorr of titanium nitride deposited at relatively high temperature, 500 degrees, and high bias of 100 eV. And you see We have columns with a lot of pores between the columns and within the columns. So this is a way to produce extremely porous films, if you like. Going down to 5 millitorr, this is an example of making use of the energy of the sputtered species. The films become dense with small grain size, but then competitive growth. But eventually they become rough with all grain boundaries. I will use this picture to the right to illustrate to you the effect of ions. Go to the next slide, please. So in the middle picture, we start with floating potential, but then we increase by 40 volts. In the middle, we go to 400 and then back to 0. And you can see this huge clear boundary is 160 eV, where the films become dark. If you look at the high amplification to the left, the bottom we see porous grain boundaries, and as about 120 volts, these pores close, but we also see these speckles in the side the grains, and this is because ions penetrate into the lattice. They cause collision cascades, which cause densification, but also there's a trap residual damage and trap argon. And at 160, this is very much, as you can see in the right picture, pronounced. And eventually at high voltages, we get renucleation. So that's the price we pay for densification by ion bombardment. If you look at the graphs, we build in stress in the films, out of plane lattice constants become higher. And in the bottom graph, we trap a lot of argon, several percent. And if you go to 1700 volts on the right picture, you see a lot of gas bubbles. So bias sputtering is useful if we maintain the energy as low as possible in the range of 100 eV, depending on the plasma density, at the expense of this kind of residual stresses on the order of several gigapascal. So if you go to the next slide, I introduce to you the titanium aluminum nitride, which has been used for now 30 years as an improvement on titanium nitride as an oxidation resistant coating and hardening, which I'll also talk about. As soon as it grows into the cubic phase to the left, it is identical to the zone 1 structure that I showed you. Behaves just like titanium nitride. If we apply bias at 150, we get this renucleation. So densification, again, comes at the expense of discharge gas incorporation, lattice defects, and compressive stresses. Next slide. Now, some 25 years ago, we introduced this high power impulse magnetron sputtering. The first paper, Vladimir Kuznetsov brought this power supply to Linköping, and in the group of Will Helmersham, we did some measurements of this discharge. And what it came out is that we can have peak current densities 3 orders of magnitude higher than in conventional magnetron, and also that the ionized fraction is up to 70%. So the message was that this is a technique for producing metal ions. Next slide. The second paper gave a little bit more insight into the discharge. So to the left on the screen, the discharge extinguishes between the pulses, So we have high voltage breakdown of the discharge, and then the voltage goes to magnetron, typical magnetron type voltages. There is a huge peak in the discharge current. But by optical spectroscopy, we see that there is a transition from argon-dominated region to metal-dominated region. So we concluded that this time separation between argon and metal-dominated fluxes at the substrate opened up the possibility to select one of the components with a suitable synchronized bias. And this is what next slide, we have been exploiting with Gregorz in the last decade for metal ion assisted growth. And these are ion mass spectroscopy measurements for reactive sputtering, comparing the more reactive group 4B metals, titanium, zirconium, and hafnium, with less reactive group 6B, chromium, moly, and tungsten. And we see that in the more reactive species, there is an overlap between argon and metal ions. So it's a little bit more difficult to select the metal ion dominated. In the 6B, the metal ion dominated stand out. And the other observation is that the heavier the metal, the more dominating is the metal ion phase. This is because of gas rarefaction. The metal ions push away the argon, and the discharge in the metal ions is more pronounced. So next slide illustrates how this data can be used to select the metal ion assisted growth. Next slide. So this is one of the earliest papers by Helmershon showing that because HiPIMS produces energetic ions, even on grounded substrate, it is capable of producing dense films. And on the right, you can see that the cost of this is the deposition rates are lower because some of the back attraction of the positive metal ions to the target. And this is for all targets. Next slide. Now, for the rest of the talk, I'll use a hybrid HiPIMS DC magnetron sputtering configuration where we use metal ions from the HiPIMS discharge and the high deposition rate from the DC magnetron sputtering. And the first half of it will be dealing with producing highly supersaturated metastable cubic transition metal nitrides using light ions, aluminum and silicon. Next slide. Now, I want to devote a little bit more attention to titanium aluminum nitride, which is metastable. The aluminum nitride and titanium nitride is immiscible even at 1,000 degrees Celsius. However, the cubic titanium aluminum nitride, which is desirable, can be produced in a metastable phase up to 2/3 with aluminum nitride by PVD as oxidation resistant and wear resistant coatings. I mentioned that the cubic phase behaves like the titanium nitride. On the right image, the temperature is 560, and we have significant ion bombardment. So the films that grow on MgO start, these black areas are epitaxial, but Wurtzite aluminum nitride comes out down epitaxy. We have columnar growth, but sensitive to very small amount the tungsten of the cubic, the wurtzite aluminum, that as a detection for the phase separation. Next slide. Now, another kind of characteristics of titanium aluminum nitride that I would like you to introduce is, if you look at the lower curve, titanium nitride, if we anneal titanium nitride, these stresses that have been introduced by ion bombardment tend to anneal out. The hardness usually drops as argon diffuses out and stresses are removed. Titanium aluminum nitride actually hardens. If you look at the schematic upstairs, up in the picture, the as deposited field have random distribution of titanium aluminum, and the lattice is kind of close to strain field, strain free. As aluminum nitride tends to, like spinodal decomposition, tends to accumulate in areas, the lattice gets strained, and that causes hardening. The TM picture is actually a micrograph of such spinoidally decomposed cubic titanium aluminum nitride. You see this checkerboard pattern with roughly 2 nanometers periodicity. Then at higher temperatures, dislocations appear, and the aluminum nitride regions switch to the cubic phase, which is soft, and there is this overaging. So the drop of the hardness due to the phase separation. Next slide. Okay, now we're into the hybrid system conducted in a semicon equipment. Deposition temperature is 500 degrees Celsius. And here we compare titanium aluminum nitride deposited first by titanium DC plus aluminum HiPIMS. Then we change the targets and we use aluminum DC and titanium HiPIMS. So, and we deposit highly metastable with 60% aluminum nitride. So to gauge the ability to deposit dense films with this desirable composition. And in fact, we're comparing the effect of titanium and titanium plus versus aluminum. And that's explained in the next slide. Now, because we have this argon to initiate the discharge, and actually argon is present even in the metal phase near the target, and the argon is 50.76 eV. Titanium second ionization potential is much lower. So having titanium produces both the singly and doubly charged ions. For aluminum, the second ionization potential is almost 19 eV, so it is purely singly charged ions, while for silicon, it's on the borderline, mostly singly charged ions. Next slide. So here, to the right, the middle actually, when we use titanium and titanium plus ion bombardment, even on the floating substrates, you have to believe me, in the selected area electron diffraction, we see the aluminum, the wurtzite aluminum nitride phase on that clear ring in the middle of the diffraction pattern, and the films on the kind of right are relatively soft. These are the open signals with a lot of stresses into them. Now, the green area here in the left picture are single-phase titanium aluminum nitride. They're dense, and the phase separation comes only above 200 volts. And if you look at the hardness of these films, they go up to a maximum of close to 30 gigapascal, and at the same time, the stresses are close to zero. So stress-free, dense films produced by light ion supplantation and densification. Next slide. This is now similar results with titanium silicon nitride. Now, if we look at the left side, this is typical titanium nitride, silicon nitride nanocomposites, columnar nanocomposites. The lattice constant, which is given in the middle, is higher than titanium nitride because of the stress titanium nitride. The EDS shows that we have titanium nitride columns surrounded by silicon nitride tissue phase. So this is well known for producing hard nanocomposites. The branch where we use silicon HiPIMS to irradiate DC sputter titanium nitride is completely different. We have a linear decrease, which as a slope which coincides with DFT calculated single-phase cubic titanium silicon nitride. And of course, this is highly metastable, and we go up to almost 24%, which is one in 4 atoms of titanium has been replaced by silicon. In the cross-sectional TM, we see like columnar growth, dense film with single phase, and the images on the right are actual lattice resolution images showing the cubic phase. And in the newer versions, which I couldn't show you, actually I had included that the stresses in these films are really nearly zero. So this is another second example of stress-free films deposited that are dense under light ion bombardment, metal or silicon. Next slide. That is a work done in the group by Grzyński, in the group of Jochen Schneider in Aachen. Here they study vanadium aluminum nitride atoms and report oxidated aluminum supersaturation in single structure. Now, in the upper graph, we see the X-ray diffraction measured Wurtzite component of the films. And in the DC co-sputtering, in this case, films phase separate at around 50%. And when we use HiPIMS, aluminum HiPIMS, to produce the aluminum component, the phase separation occurs at 75 roughly %. And you can see also the hardness is very high. The examples to the left give illustrate the density of the aluminum nitride HiPIMS densified film. Next slide, please. So the mechanism of phase separation during DC magnetron sputtering with argon and nitrogen bombardment is that we have a near surface zone, which there's considerable ion mixing, which gives which produces locally aluminum nitride rich areas which form the hexagonal phase. And then it gets frozen into the deeper surface where there's no mobility. And the same similar picture applies to titanium HiPIMS aluminum DC deposition, where the titanium 2+ also induce significant ion mixing in this area. That's why we had this phase separation even at floating substrates. Now, next slide illustrates the kind of the benefit. Next. One slide before. That's 2 slides now. Okay, thank you. So here, during 95, 99% of the time, we are depositing by DC a phase reaching the stable oxide, let's say or vanadium nitride, and only in 1% or a few percent of the time, so we are depositing stable nitride, and in the high mobility zone, there is no driving force for separation because the gas ions are the floating potential around 10 eV. Now, during the HiPIM pulse, we implant the light ion into the frozen zone, so to say. We stuff it with light ion, and which does not destroy the cubic lattice. So this is the mechanism how we can produce such highly oversaturated metastable films. And the next slide is a summary of this section, which shows the completely different pathways which can be achieved by using these techniques of using light ion supplantation to deposit highly metastable cubic transition metal alloys. So next slide. Okay, now going to the second part. Low temperature growth of dense, hard, and in this case, low stress refractory ceramics using heavy metals, tantalum and tungsten. Next slide. Now, this is the thought experiments that we actually did to arrive at this idea. To the right is very light ions. They basically bounce on the surface like ping pong balls of a table. This is how we use Rutherford backscattering, for example. In the middle section is when the masses of the ions and the target are similar, we have dense cascades or not dense, cascades that are not dense and high energy recoils because of the close mass match. If we go to the left column, very heavy ions, first of all, they cannot be deflected by the light ions, so they go a straight path, and they produce a lot of low energy recoils, which we thought can be used for densification at low temperatures to substitute the thermally driven atom mobility and at higher temperature and the traditional ion-assisted growth by, let's say, argon or nitrogen irradiation. So the first experiment, next slide. The first experiment we did was with, again, titanium nitride, and we use tantalum HiPIMS. So we compare titanium versus tantalum, but we also use titanium DC magnetron sputtering with titanium HiPIMS. So we compare the effect of the mass. To the right, you see the temperature rise during such process where there is no external heating. And after an hour, DC magnetron sputtering, we reach less than 120 degrees Celsius with 5 joule per pulse. The red curve, the temperature rise is almost identical. And then as we increase power per pulse, the temperature still is below 140 degrees at the end of 1 hour. So look at the red curve. This is the conditions where we deposited the film shown in the next slide. Now, you see up there, titanium nitride without bombardment is black, absorbing. The one with 8% tantalum is kind of shiny and golden. And you can see in the cross-section the effect of starting the tantalum bombardment. So the bottom part of the film is pure titanium nitride at floating potential. And in the image B, you can see the tops of the column from the bottom interface. They're sharp. There is, and as soon as we start the tantalum bombardment, the nanoporosity in the column disappears, and the porosity between the column persists until we smoothen the top interface. When we stop the tantalum irradiation, the pores immediately appear again. Now, if you look at the hardness, the top curve, red curve, is for the tantalum bombardment. And you can see that we can reach at about 150 volts. You can reach the curve plateaus at a relatively high 25 gigapascal. If we do the same thing with tantalum, the bottom curve, we can never reach that hardness and density. So the mass of the bombarding ion really plays a key role. And if you look at the stresses into the films, up 150, 160 volts, the stresses are nearly zero. And even if we go to higher, they're below 1.5 or 2 gigapascal. So we have achieved low temperature growth of hard and dense, low stress ceramic coatings, which in addition to saving energy and time during deposition, also permits depositing such coating on temperature sensitive substrates, which take aluminum, magnesium, plastic, alloys. So next slide. Similar results with titanium, aluminum nitride, and tantalum. You can see again densification with significant increase in hardness. Next one. Now, we studied more systematically the role of the metal ion mass. And here we have these two titanium aluminum targets sputtered in DC. In the middle, we changed the metal from in group 6B, the ones that we can select the metal component by synchronized bias. Cobalt, moly, and tungsten. So the upper left plan view TEM, you see huge porosity, which kind of disappears when we go to the heaviest metal. Now we evaluate or quantificate the porosity by measuring by XPS the oxygen content in the films, which is this CO in the upper left here corner noted. And for the open DC sputter film, this is 3.8%, very low hardness, low stress. When we go to cobalt, this is oxygen which is absorbed into this voids after deposition. We get densification, reduce of the oxygen content, increase in hardness, a little bit more for moly. But when we go to tungsten, you see oxygen content is below 1%, and this is probably due to the background pressure during deposition, which we cannot avoid, and the hardness is highest, and the stresses are relatively modest. Next slide. Now this can be understood by or some light by looking at the stream Monte Carlo data. The cascade by chromium, the upper left, you can see it is chromium implantation is about the same as the recoils of titanium, aluminum, and nitrogen, about the same. As we go to moly and tungsten, the heavy atoms are deposited beyond the area of mixing, so they cause additional densification. And you notice that the difference between the number of nitrogen atom and metal ions becomes significant. So the nitrogen sublattice is almost undisturbed by heavy metal ion bombardment, and that helps stabilize the cubic phase. If you look at the energy distribution of the particles, the top graph, you can see the chromium extends to very high energies because of the high mass. And then if you look at what is this, yellowish color, the tungsten, it is low energy and high number. So larger penetration depth with tungsten, nitrogen lattice almost intact. Look at the bottom curve, nitrogen almost no displacement in nitrogen, and large number of low energy ions. So these are the benefits, specificity of using heavy metal. Next one. Next one. Okay, so here now we studied the effect of metal ion dose, again with titanium aluminum nitride, and bombard with tungsten. And the way, so what do we mean by ion dose? So it is related to the tungsten fraction, X, which is the quantity, the amount of tungsten into the film as a fraction of the total metal amount. The ionized fraction of tungsten is unknown. It's about, let's say, 50%. But then, so the ion dose is half of X. And then the ion energy is proportional to X and the voltage applied, while the momentum is proportional to X. That's missing in this slide. times the square root of the voltage. And here we varied the X by keeping the peak current the same, but we varied length of the pulse from 20 microseconds to produce 0.2 here, X 0.02, to 100 microseconds pulse length. Of course, that increased the power of the HiPIMS pulse. And then we get the green curves, which is 0.12. Now, if you look at the oxygen concentration, the top graph, with small x 0.2, we never get densification when we increase the energy. And if we go to the blue and the green curve, we get densification at about 100, 120 volts. The hardness, which is the middle panel, is high for the higher amounts of the higher dose. And the amount of tungsten never get high hardness. The panel to the right compares the oxygen content or density versus hardness. And you can see the density and hardness go hand in hand. So the dense films are hard, the porous films are soft. The bottom panel shows the stresses into the films. So with having high dose and high energy, we actually introduce quite a lot of stresses. So there has to be optimum here between dose and energy. So let's look at the next slide. So all of this data here is mapped. The bottom axis is the voltage or the energy. The top panel is for stresses. The left axis is dose or the X. So if you look at the stresses, the light blue, which is the top panel is the oxygen content or the density. The light blue is below 1%. So these are the dense films, and they have this behavior where and the bottom graph is for the stresses. And again, the light blue zone is about below 1 gigapascal. And you can see that they overlap, they are the same. So there is a range of an area where we can produce dense and stress-free films that are hard. Next slide. Here we try to compare the momentum and the energy. The same data for the oxygen content or the density in the film plotted as a function of deposited energy. It is much more scattered than when we plot it as function of deposited momentum. And there is a critical value of arbitrary unit x time a point or square root of v of 1.2, where we can choose dense and dense film. And by looking at the previous map, we can choose dense films with relatively low stresses. Okay, next slide. Now, I mentioned that working at low temperature, in addition to being able to grow films on temperature-sensitive substrate, it saves time, and energy. The top red kind of estimate is the energy consumption in a normal cycle at 500 degrees Celsius for DC magnetron sputtering titanium aluminum nitride. Heating, pre-deposition heating usually is 2 hours at these kilowatts. This is heating, preheating, and the DC power of the targets, it comes almost to 23 kilowatts hours. Now, the blue estimate downstairs is that we are preheating for just at much lower temperature than power. Then we turn off the heat and for 1 hour for the temperature to go down to, let's say, 50 degrees. And then we start the same DC power, but also we add the power of the target, and it ends up like 7 kilowatts hour. So this is an energy saving in about 80%, which is the subject of this kind of paper, a few papers by Xiao Li, a part of her thesis. And also time for shorter cooling down and shorter preheating. The next slide. Now, all of this so far was on stationary substrates, the upper left diagram. Of course, for most applications, one needs rotation, and this is an estimate of what are the problems that occur in one-fold rotation. And here we have two sets of targets on both sides, and we have a certain amount of material deposited by DC wind, which then has to be densified by heavy metal ion bombardment. And you can see that with low ion energy, like the floating potential, we have multilayers. And the multilayers are preserved even at 180 volts. And if you can look at the satellites around the main 111 peak, the satellites disappear above, let's say, 300 volts. So we can produce, we can smear out the multilayers, provided that the range of implantation of heavy ions exceeds the deposition stresses into the films. They do become kind of above 1.5, but the films are hard, and they are dense and low argon incorporation for energies of about 200 eV. So there is a optimum energy that can be used here. Next slide. So we wanted to study the thermal stability of these films, and here we have titanium aluminum nitride, the red curve. The red curve is aluminum nitride rich 62%. This hardening and softening, just like for titanium aluminum nitride, and the diffraction pattern, the TEM shows that these films do have at 900 degrees aluminum nitride phase separation, but also BCC tungsten. The dark spots, which is only 40% that are more stable only 40% aluminum nitride, there is no softening. So that was puzzling. Next slide. Here we zoomed in, and what we saw is all of these single atom thick discs of tungsten on 111 planes, and these are they're analogous to the Guinier-Preston zones that were discovered in the 1930s by Guinier-Preston in soft aluminum copper alloys, demonstrated to the right. For the aluminum and magnesium alloys, these occur on 1001 cubic planes. In our coatings, they appear on 111. So this is the first time, to our knowledge, reported for refractory nitrides. Next slide. Okay, now having understood what this is, we looked back at some old papers. We see similar ordering, so we are going to study this a little bit more detail now, and the combination of stable cubic nitrides and with metals that are forming not so reactive, like moly, tungsten, tantalum. These are the possible candidates. So next slide. So this is like a summary. We have two branches here. Light metal ions allows us to use supplantation, supersaturated films, and we actually have some examples on diborides. On the right-hand side, the heavy metals, and again, we have some interesting results on diborides. Next slide. This is my last slide. I want to thank all the co-authors in the cited papers. These are some review articles that you can find most of what I talked about, and you can contact me if you have anytime by email if you have questions. Thank you very much.
Hello.
Thank you, Ivan. Apologies for the connection issues, but I think we did okay in the end there. Which we didn't have the exact up-to-date version of the slides, but I don't think that was a problem. We're going to be running a little longer than our typical 60 minutes just to ensure that we cover everything. So what we'll be doing now.
Perfect. Thank you very much for the nice introduction, and also a very warm thank you to Professor Petkov for the talk. Great. Thank you very much. And I want to now take a couple of minutes to introduce our company, Data Physics Instruments. And we are a manufacturer of the measurement equipment that can be used to study interfaces and surfaces. We are located in the southwest of Germany, and we are now around 45 people.
A couple of questions,
and around 1/3 of these people is working in our development department. So you see, this is a very development intense work that we are doing here. And we are active in the field since 25 years and present in around 80 countries worldwide. So we have now reached a size with 45 people where we have very economic, I would say, standard solutions, but we are still small enough to also serve customized needs. So if the people then need special stages, heating equipment, or so on, we are always very happy to collaborate and develop a dedicated piece of equipment for these users. Maybe to show you a little bit what we are doing. So we have here this kind of contact angle analyzers. These contact angle analyzers you can have for pressures up to 750 bars and temperature up to 1800 degrees. We have the force tensiometers that can be also used in order to study adhesive properties on solid substrates. We have the dispersion stability analyzers. So if you want to know how stable is a certain formulation, it can be a suspension, it can be an emulsion or even a foam. This is the right piece of equipment. And if you want to go and do different types of measurements at a certain humidity, we also have this kind of humidity generators and controllers. Quite recently, we added to our product portfolio a device that can be used to measure the setup potential on extended solid surfaces. So if you want to do a coating on wafers, for example, on a glass slide, or you want to study filtration membranes or the metal grids or so on, this is the instrument of choice to do the setup potential analysis. And in addition, we have the spinning drop tensiometers to measure the very, very low surface interface tensions. Today, I want to show you a little bit how optical contact angle analyzers are working and what can be done with these. So these instruments, they are there in order to characterize liquids regarding their surface tension and interface tension, but these instruments can also be used in order to characterize solid surfaces. So you can characterize the solids regarding their wettability, static wettability and dynamic wettability, but you can also do, for example, surface free energy analysis or work of adhesion analysis. So this is all possible with the same device. To quickly introduce, you see here, this kind of devices, they need a camera system and opposite the camera system, a light source. And here you have a sample stage and a dosing unit. So what we are doing is we are basically studying the shape of a drop on a solid surface or at a needle tip. And if we study it at the needle tip, then we are studying the liquid's surface tension or interface tension. If we study the drops on the solid surface, then we want to know the interaction between liquids and solid surfaces. In these pictures here, you see a couple of examples. So the first picture here, drop hanging at the end of the needle. This is typical measurement for surface tension. Then you see here, you can even immerse samples under a liquid and dose a second drop on it. So you can study, for example, how is oil interacting with core rock in an environment of water with emulsifier, for example. We can do very, very nice things like measuring here a contact angle on a bent surface like a wedding ring. And this kind of equipment is available in many, many different variations. So this is modular systems. And what I want to show you today, I want to show you a little bit how modern types of contact angle analyzers are able to even measure if you have only very, very tiny surfaces available. Maybe you only have 1 square millimeter available, but it's still enough to characterize the surface. I want to show you this a little bit with a small example, but before we do this, a bit on wetting properties. So when you are bringing in contact a liquid with a solid surface, then you have the so-called 3-phase contact point. This is the point here, where you have the solid, the liquid, and the surrounding environment, which is typically air. And then you can do a static droplet on the surface that is not moving anymore and determine its static contact angle. And now we are distinguishing. If the contact angle is 0, you have a complete wetting on your surface. If the contact angle is below 90 degrees, then we are talking about good wetting properties. And non-wetting at all, we are talking about if we are approaching with our contact angle to around 180 degrees. So this means from the picture seen of this, from the side of the droplet on the solid surface, we can basically quantify how well wettable the surface is. And from these wettability parameters, we can, for example, calculate the polarity of the solid surface. You can then judge whether a plasma treatment was successful or not. Plasma treatment makes the surface more polar. You can judge whether a coating was applied successful and probably even whether your sputtering process was successful or not. So it's applicable basically in any field you can imagine. I want to show you now with a little application example what is possible with modern technology. So as little example, we take this PCB board. And we have different locations on this PCB board where we want to judge how good is the wettability. Was it cleaned well? Was it coated well? So we want to do this on the rear side of the substrate here. But there we have a relatively big area available, 4 millimeters on 4 millimeters. We want to do it here in area number 2 in this bonding position. There we have only around 2.7 on 3 millimeters available. And then we also want to do the same analysis here in this region where we only have these tiny pin surfaces available. They are only 200 micron wide and 1.3 millimeter in length. And here in this table, you can judge a little bit how small your droplets need to be in order to conduct this measurement. So we have divided it into 3 sizes: conventional dosing in the microliter range, nanoliter dosing, and picoliter dosing. And you can see, depending on the expected contact angle that you will get on this kind of surface, you have to choose the volume. So just imagine if you have a system that can dose 10 nanoliter, the expected contact angle is around 90 degrees, then you are good to measure on an available surface area that is probably only 200 micron wide. There the drop can fit in. And I want to show you this now with a couple of practical pictures. Let me go one slide further. So example here, look, we are measuring with a simple needle-based system. This is the standard systems for contact angle analysis on this PCB board. Volume is around 1 microliter, and this is the droplets picture on the surface. Very simple, possible to see from the side, contact angle around 55 degrees. What happens if we want to measure in these areas here, area 2, for example, then we should change our dosing system and we should go for a nanoliter dosing system. And in this case, you can see we have been using a nanoliter dosing valve and make a tiny drop that is only wetting this area here. Yeah. I show you here also on the next slide. If we want to go even smaller and measure on this tiny golden contact areas here, then we need to shift from a nanoliter dosing system to a picoliter dosing system. You see the system here, you have tiny disposable cartridges inside this measurement head. And this measurement head is actuating this cartridge by setting a pulse on it. And then through this kind of cartridge, it has a tiny, tiny nozzle on the lower end. A droplet is coming out. And these droplets, they can go down to 30 picoliter. And when this 30 picoliter drops here, you can see them in the picture, they have a diameter that is significantly lower than the 200 micrometer that we have available here for the surface area. So you can see this on the picture lower right side very, very nicely. You have here golden pin, then you have a cavity in between, plastic surface. Then you have the next golden pin, and this kind of systems can be programmed in order to measure on all of these pins automatically after each other. And we measured on these pins, I think it were 14 if I remember it correctly, and the difference in the contact angle between these pins was only around plus minus 1.2 degrees. So you can fully automatically measure on this kind of tiny available surface area and then assess whether these are cleaned or coated nicely, homogeneously. So I only wanted to show you a couple of very, very short slides to indicate to you, okay, contact angle measurement, this is a very simple destruction-free method that you can use to quickly characterize whether your surface was successfully coated or treated or not. Yeah? And if you have any questions, I'm very open for them. And if you have any samples that you would like to measure and try out, our application lab is also very, very happy to work on this together with you. So thank you very much for listening and looking forward to your questions. Thank you. Good.
Well, we can never have zero, as long as it is not due to porosity. I think if we want to dope with oxygen, there's a lot of application of oxynitrides, and they have properties, but these are dense coatings that have oxygen. So do I understand your, so oxynitrides, oxyborides, if you like, no, oxyborides haven't been studied, but oxynitrides are studied. So intentionally introducing oxygen to improve properties is being done, but not unintentionally due to porosity. We want to have dense films in general, unless you want to have surface area, but that's a different thing. He said advantages from non-zero oxygen. So that means he wants to have some oxygen. Yeah. Tribological in terms of friction coefficient, we haven't studied them. We have studied, let's say, adhesion. We have studied ductility, crack propagation, but not tribological. And in general, dense hard coatings. One of the examples that I didn't have a chance to talk about, the zirconium tantalum boron nitride has this core shell structure, columnar, which has very hard diboride columns surrounded by amorphous metal-like columns. They are hard and ductile. So there are a lot of interesting properties, mechanical properties, but tribology, I don't think we have studied tribological properties. They should be similar, I don't know, like vanadium and aluminum nitride is known to be high temperature, low friction coefficient because of forming Manelli phases. So just the general applications of hard coatings.
Sam, you are asking Professor Petrov, or? Okay.
Asking me? No. Unfortunately, no. We should do that with Sebastian.
Happy to do so.
Oh, I think we'll continue at IUVista, as I'm involved in the self-engineering division of the International Union Vacuum Science Technology and Application, which has allowed 33 countries, 34, 35. And next workshop that we're organizing in Germany is called Surface Engineering for Sustainable Development. It's not exactly that title, but we are asking questions. How can we save energy? How can we save a material? Do we need that high purity material? Do we need these all complex alloys, or can we work with cheaper materials, less materials, and achieve save energy and achieve the same goals? So that's one of the directions that we're going. Sustainability goals, sustainable surface engineering, and that's important. I can share the. I mean, if you Google that, IUVista is the 100th symposium of IUVista. So I think that is a future direction that we actually established a new division on sustainability in IUVista to achieve these goals for better. Otherwise, the complexity will continue growing, and we will grow. I mean, the synthesis or deposition techniques continue to grow, to develop. The complexity of the coatings will go, but also we have to think how we can make them cheaper, save materials, and save energy.
Thanks, Sebastian. Great presentation. Good, very good summary of the capabilities of the equipment. It's very interesting to see the application on specific electrical connectors there. I hadn't really seen that previously. Okay, so now what I'm going to do is release the featured action for the attendance certificate. So for those of you that are still here, if you would like the attendance certificate, please go ahead and click on that link. It will remain active for the next day, so please don't close down this tab. We'll still be going for a few minutes whilst we deal with a few questions or any comments any of the audience members have. Okay. So let's begin. Ivan, we've got a question here from Andre, who asks, thanks for the talk. Do you see any possible advantages from a non-zero oxygen concentration in the composition of coatings? For example, could it enhance thermal stability, cutting performance, or tribological properties?
Thanks a lot. Bye-bye.
Thank you. Bye.
I think Andre's trying to say, are there any advantages of specifically trying to remove oxygen from any coatings? but I guess you said normally you would add it for more specific properties. Sorry. Yes. Got it. Sorry. Okay. If there are any other questions, please, we'll be here for another few minutes. Please type them in the chat. There was one comment earlier from Alexi, who did say it would be interesting to know more about some properties of the films that you've discussed today, maybe tribological in comparison to standard PVD of, say, a standard titanium nitride. Ivan, has there been any work on that, or is this very much initial film development? Mm-hmm. 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 Okay, thank you. Seems we don't have any other questions from the audience, so perhaps we can just do a couple here, if that's okay. One of the things since we have Sebastian here, has there been any study of the change in wettability or surface free energy of those coatings that you've discussed today? Has that been something you've considered yet? Yes, just asking, just to see if there has been any any study of. Yes, have you any study of the surface free energy of the coatings and how that may change? There we go. Well, it would be very interesting to see, I'm sure. And I think we'll just round out with one kind of final question for me, Professor Petrov, just on where do you see the field of thin films progressing in, say, the next 5 to 10 years with the innovative work that you're doing? Do you think it's going to be towards dense stress coatings? Do you think it will be more multi-layer? Where can you see surface engineering going? Oh. There we go. We're back. Mm-hmm. 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 Mm. Yeah. Mm-hmm. 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 Okay. Thank you. Yeah. Yes, I'll contact you later about that symposium. I think that might be quite interesting for us to feature in our newsletter in an upcoming issue. But I think with that, we've now reached the end of the webinar. So with that, let's bring up our closing slide. I'd just like to say, Ivan, thank you very much for your fascinating presentation today. Lots to think about, lots of papers to go read and find out more about. Sebastian, thank you very much for your presentation, and thank you, Data Physics Instruments, for the support for our keynotes. We wouldn't be able to do what we do without the support of our kind partners, so thank you. As a reminder, of course, please visit our website, surfaceventures.org, for information about our upcoming talks. You can see recordings of our previous talks as well. In terms of upcoming talks, we have just shared on screen now Professor David Noel of Imperial College London, who will be delivering our next keynote on the 29th of February. That will soon be on our website as well, so you can register for that. You can click on the registration link there now. As well, we have our fortnightly newsletter, Modern Surface. If you sign up to our mailing list, you will receive this. And finally, I'd like to ask everyone in the audience, please do advertise this to your contacts. It would be great for us to continue to grow. And with that, I'd like to say thank you all very much, everyone, and have a great rest of your day. Thank you. Thanks, everyone. Bye.